Okay, so while you're all wrestling with complexity, and we just had a little wrestle with complexity up there, I see, we've been wrestling with consciousness. So I'm going to talk about consciousness through a theoretical computer science lens, and this is joint work with Manuel Blum and Avram Blum. And after I do my introduction, Manuel hopefully will get up on stage and his slides will work as well. Okay, so the study of consciousness has been the purview of philosophers and theologians throughout the ages. Until about 30 years ago, the scientific study of consciousness was essentially taboo. That changed with the advent of fMRI technology in the 90s because that enabled neuroscientists to look non-invasively in the brain and see what was happening when people were thinking different thoughts, when they were doing different activities. So now consciousness is being studied by scientists and of many stripes, and we're looking at consciousness from the perspective of TCS. So I'm going to talk about the Conscious Turing Machine, which is a TCS framework for a conscious artificial general intelligence, AGI. And of course, the Conscious Turing Machine is inspired by Alan Turing's simple yet powerful model of computation, and also Bernard Bahr's global workspace theory of consciousness. So Bahr describes conscious awareness through a theater analogy. And what Bahr says is that consciousness is the activity of actors in a play performing on a stage of working or short-term memory. The inner speech actor is often on stage, and this actor's performance is under observation by a huge audience of unconscious processors in long-term memory that are sitting in the dark. So I hope you guys aren't sitting in the dark too much there, but you're like my long-term memory processors. And what Bahr says is that some members of the audience want to get their information on stage for the actor to broadcast to everybody, and they have some kind of discussion to decide what's going on stage. So I'm going to go with a little example that you may be familiar with. Perhaps it's happened to you once or twice. You're at a party, you see somebody you know, but for the life of you, you can't remember their name. But then what happens is about an hour later, you're home, and somehow that name pops up into your consciousness when it's too late to do anything about it. So what's going on? So what's happening is one of your unconscious processors, one of those in the audience, is really embarrassed when they see this person that they can't remember their name. And it sends up a message into a competition to get on stage with a lot of weight. So it gets up on stage, what's her name? And as soon as that is up on stage, it gets broadcast to all your long-term memory processors. And then perhaps one of the processors in your long-term memory recalls where you first met. Perhaps it was in a computer science class, and that has some weight to it. It gets up onto the stage and then gets broadcast down. Another processor with those priming remembers something about what she does. Of course, she works in complexity theory. That gets up to the stage and then gets broadcast down. And another processor says her name begins with T. It gets up to the stage, broadcast down. And a while later, another processor says, no, her name is Sarah, and that is her name. It comes up to the stage from the audience of unconscious processors, long-term memory processors, which have been thinking, searching. So the conscious self on stage doesn't know how or where her name was found. It seems to just pop out of nowhere to you. But every so often you will hear what the name of the spelling of her name or something like that where you first met. Okay, so now I'm going to give you our formal conscious Turing machine structure and its dynamics. But before I do, I'd like to say what it is not. So the Conscious Turing Machine is not a model of the brain. It's a simple machine model of consciousness. It considers the brain at a very high level of abstraction, at levels well above that of neurons and neuronal activity. And I say it's above the fray because we're not saying where this is happening particularly. And also the CTM is not a standard Turing machine. What gives the CTM the feeling of consciousness is not its input-output map, nor its computing power, but what's under its hood. And what's under its hood will be a global workspace architecture. We'll sort of outline that. Something that we call predictive dynamics. And these are cycles of prediction, feedback, and learning that are happening throughout the machine. And then some very special key long-term memory processors, inner speech, inner vision, and the sensations, but in particular, the model of the world processor. And these processors communicate in a rich, multimodal inner language, which we call brainish. And of course, we pay attention to resource limitations, both with respect to the construction of the CTM and the explanations that it gives. So the CTM, the Conscious Turing Machine, is defined formally as a 7-tuple, STM, LTM, uptree, downtree, links, input, output, and I'm going to give you a sketch of each of these. So here we have the Conscious Turing Machine sketch, and we start with a very tiny short-term memory. It's a read-write memory, and that memory, that's our stage, and it can hold one chunk of information. Shortly, I'll tell you what a chunk is, but in the literature, they say that maybe we can hold 7 plus or minus 2 chunks of information at any one time in our consciousness. And because we're trying to simplify and we can get away with it, we're assuming just one chunk of information at any time in the short-term memory. And then we have a very large collection of long-term memory processors. That's our audience. And we are assuming maybe 10 to the 7th processors. That's because there are 10 to the 7th cortical columns in the brain. And these processors are very powerful. They're parallel at first, they're unconnected. They start off that way. Some of them have designated processes that they're doing that are built in, and others are just powerful processes that haven't been designated yet. Okay, so that's our audience. We have our stage, our audience. We have input maps coming from the external world through sensors like eyes, ears, nose, and touch. And that input is going directly to some specialized processors. We have output going from some specialized processors to actuators that then will affect the outside world. Okay. And at every clock tick, every member of the long-term memory processors, every member of the audience is putting a chunk of information into an uptree competition to get onto stage. And I'll talk a little bit about this competition in a moment. But as soon as that chunk gets up on stage, it's being broadcast to all long-term memory processors, and all long-term memory processors get this chunk of information. So immediately we can start to give some formal definitions. We'll say that the conscious content of the Conscious Turing Machine at time t is that chunk in short-term memory at time t. So in other words, it's the winner of the uptree competition, and the CTM is consciously aware as soon as all of its long-term memory processors received the broadcast. So conscious awareness is the reception of the broadcast of the conscious content by all long-term memory processors. These are just definitions, but we'll come back to them soon. Okay, so we've looked at short-term memory, long-term memory. So we mentioned the uptree, we mentioned the downtree. I'd like to talk about links. So as I said before, these processors start out, the baby CTM has these processors and they're totally unconnected. But after a while, connections start to form. So when one processor realizes another processor has relevant information or one it wants to communicate with, it will form a link, a bidirectional link between those two processors. So for example, in the what's her name scenario, the processor that asked the question, what's her name? And then the processor that gave her name as Sarah, those processors will link. The processors will link together by a bidirectional link. So what's going on now is this is how communication between processors changes from being conscious communication to unconscious communication. So for example, when you're learning to ride a bike, all of your processes, all of your thinking, movement, and all that is very conscious. But after a while, with a lot of practice, links are being formed between the various unconscious processors, between your motor processor and your vision processor, and so forth. And so a lot of the communication now is just done unconsciously. There's another little interesting aspect to this. Alison Gupnick, who is a psychologist who works with babies and infants and young children, she often says that infants are more conscious than adults. Now, that seems so preposterous, really totally doesn't sound right. But in our model, it seems perfectly reasonable because our baby CTM, our infant CTM, has no links, of course. So all the communication has to go through the short-term memory, through the stage. So all the communication is conscious. And after a while, as these links form, some of that communication then becomes unconscious. And that may be a way of understanding what Allison is saying. So when these links form, how do these processes talk to each other? So we have a very rich multimodal language, which we call Brainish. And Brainish is very different than an outside language like English or Chinese. Each word in Brainish is a combination of maybe images, sounds, sensations, smells. So for example, if you have the word rose, you may also in that Brainish word actually see an image of a rose. Maybe it will be red, and you'll have a sense of its smell, and maybe something about your feeling of happiness when you do that. And that will be all condensed in a succinct Brainish word. We have a student at Carnegie Mellon who is an expert in multimodal machine learning, and he's developing a Brainish for our Conscious Turing Machine. Okay, so now really one of the important parts is how does this competition work of getting information into short-term memory? And so I'm going to discuss that for a little while. So vaguely, Bars says, oh, they discuss between themselves, the processors, and they get some information up. But we want to formalize what's really going on. So we have a binary uptree, and that's where our competition is. And at each moment of time, each processor puts a chunk into the competition. So let me tell you what a chunk is. A chunk for us is formally a six-tuple. Now, in the literature, again, a chunk is very informally defined. It's a little bit of information. It's a phrase. It's something like that. We formally define chunk this way. It's a six-tuple. The first four parameters of that six-tuple are the most important for this chunk. It gives you the address of the processor that put in the chunk into the competition. So if there are 10 to the 7th processors, this is just a 7-digit number. The time the chunk was put in. The gist is the information that the processor wants to convey, or a question like, what's her name? And it's the weight that the processor attaches to that gist. So if it's what's her name and it's very embarrassed, that weight will have a high absolute value and it might be a negative weight. So weights can be our valence, positive or negative. And then there are two other parameters that we have in here that I have in green, and they start out, the intensity starts out as the absolute value of weight, and mood starts out as weight. And as a chunk progresses in winning the competition at every stage, what will happen is the first four parameters will stay the same, and the last two parameters will be changing. And they'll be changing to get more global information. So again, the gist is succinct information in Brainish, and the weight is the importance value of confidence that the chunk, that the processor is giving to that chunk, and it's also could be valenced. These chunks compete locally, and the local winner moves up one level. So here I'd like to show you a bit about how the competition works. Here we have chunk C1 and chunk C2, and they're up at some level. And I want to see how it goes up one more level. Up till now, everything I've said, it talks about the deterministic CTM, but we have now added some probability here. And at each node in the uptree competition, we add a coin flip neuron. And what the coin flip neuron does is it takes two non-negative numbers, A and B, and it'll output A with probability A over A plus B, and B with probability 1 minus the probability of A. Now, why are we doing this? I think Manuel will go into more detail about why we're doing this. But for one, we found that without having this coin flip neuron, without having any probability, it was very cumbersome to get the kind of results we wanted. And the moment we did this, everything came out very simply and naturally and really nicely. So I'll tell you a little bit about that. So let me tell you how the competition works. And I'll give you one example of a competition function. And we'll start with what we call, I'll give you the competition algorithm, but we start with a competition function. And in the simple case of the function on the chunk will be just the intensity. And that's one of the two parameters at the end there. And the competition algorithm will be the following. you're given two competing chunks, C1 and C2, and you're going to input the intensity of C1, the intensity of C2 into the coin flip neuron. And then CI or C1 or C2 is the local winner with probability the intensity of C1 over the sum of the intensities of C1 and C2. And the winner will have that same probability. So we'll have the first. So if CI has probability f of CI or f of C1 plus f of C2, the winner will have the first four parameters, PI, T, the gist I, the weight I. So those parameters will stay the same. And then the last two parameters will be the sum of the current intensities of C1 and C2 and the current moods of C1 and C2. So what's happening here is actually, even though the decision is being made locally, these screen parameters are really gathering more and more global information as chunks are moving up in the competition. So there's the winner. And that means, by simple induction, is that the probability of a chunk C winning the competition is, in this case, the intensity over the sum of the intensities of all the chunks that were put into the competition. And what that actually has a nice property, it's independent of the location of the processor. So this is really nice for us, because if you have the brain or a machine, you don't want to have to move processes around depending on their rankings, like you might have to do in a chess or a tournament or a tennis match, where you don't want to, you seed players, so you don't want to put the two top players to start together. So you're moving people around all the time. But in our case, we don't want to do this, and it has a nice property that this competition algorithm will give a winner, which is independent of the location of the processor. And we have a general competition function. It's a little bit more complicated. Manuel will talk about that. And what's nice about the general case here, it's basically, if you want to have independence of location of its processor in the competition, it has to look more, the competition function has to look a little bit more like this. And there are a number of implications of this, which I believe Manuel will talk about. Okay, so now we have the up tree, down tree, links, input, output, all of that. Let me say a little bit more about long-term memory processors. I'll say a little bit more in a minute, but just to start, embedded in each long-term memory processors is one of Manuel Blum's sleeping experts algorithms. This is a learning algorithm. And so what's happening is these processors have to know how to weigh their chunks, their gists that they're putting into the competition. And so these sleeping experts algorithms help balance the CTM in general. So remember, there's the processor that said her name began with T, but actually her name was Sarah. So its sleeping expert algorithm will say, hey, you gave too much weight to you're thinking that her name started with T. It got into short-term memory, but actually found out you were wrong. Her name was Sarah. Kind of cool it, lower the weights, lower the absolute values of weights that you're giving chunks for a while. And then there was a processor who actually said her name began with S, but said it kind of timidly, didn't put enough weight to that. And so it didn't get into short-term memory, but found out later that it was right, that her name was Sarah, and its sleeping expert algorithm will tell that processor, hey, don't be so timid, give some more weights. You're kind of, you're on the ball. Yeah, give some more weights to your chunks, to the gists in your chunks. So this sleeping expert algorithms helps balance what's happening in the conscious Turing machine. So now we can see we have some of this predictive dynamics going on, cycles of prediction, feedback, and learning. So when processes put chunks into the competition, you can think of sometimes those are like predictions. When they send information to actuators to do something in the outside world, that can be thought of as predictions. When they give information to other processors through links, you could think of that as prediction. They're getting feedback from the broadcast. They're getting feedback from input from the external world. They're getting feedback from other processors. And then there's the learning that's going on. And so there's some of this kind of global, what we call predictive dynamics happening. Okay, I already gave you formally 2 definitions. What's the conscious content at time t? That's the chunk that's in the short-term memory. What's conscious awareness? That's the moment when all the processes receive the broadcast. We could add another definition, the stream of consciousness, and that's the time order chunks that are broadcast from short-term memory to long-term memory. So James had a had a definition of stream of consciousness. We can have a formal definition in our model as well. But again, these are just definitions, and the reasonableness of our definitions of consciousness will lie in the number of concepts that the model exhibits or explains easily and naturally. And we have quite a few of these examples by now. I'm going to give you 3. These 3 I'm giving you, and our explanations will agree at a very high level with the cognitive science literature. So the 3 I'm going to give you are 3 examples that are typically used when people are explaining consciousness. So in Stanley Haynes' book, for example, the first 3 examples, I think, are these examples. So oftentimes one learns something about neuroscience through pathologies. Here we have a pathology. This gentleman it's called blind sight. And this gentleman claims he's blind. Maybe at one time he could see, but he claims he's blind. So he's asked, or let's think of him as a CTM, is asked to go to the other room. And he says, but I can't see. And here's this cluttered room. But nevertheless, he gets up, walks to the door, avoiding all the obstacles. So what's going on? Let's see what we can give as a CTM explanation. So as I mentioned, we're assuming that this gentleman or the CTM here had sight at one time. And so at that time, his vision processor had formed links to the motor processor, which had outputs to the external world through, let's say, the leg or other actuators. Okay, and those links had already formed. So in this example, we have an input coming from the sensor eye to the vision processor, and then the vision processor, which is working properly, sends messages via link to the motor processor, which sends messages to the walk actuator, and the guy starts walking. But the connection from the vision processor to short-term memory to the stage is broken, or it doesn't exist. And without the vision processor having access to short-term memory, the CTM has no conscious sense that he can see. So the explanation, which agrees at the high level, is branches to short-term memory are damaged, but the processors and links are functioning. Here's another example which you may have seen. We have these people passing. There's a film here, and these white-shirted players and dark-shirted players are passing a ball, and the viewers are asked to count how many times do the white-shirted players pass the ball, and most people get it correctly, 15. But why didn't we or CTM see the gorilla, which is there right in plain sight? So if you've seen this before, you actually see the gorillas, but you haven't, you don't usually see this. And what's going on when the CTM is given a task to do, it gives higher weights to that task, in this case white, and it won't be conscious of other things that are given lower weights. So the weight here is very important. So it's the power effect of weights, and it's consistent with explanations in humans that inattentional blindness can serve as a filter for irrelevant information. It may also filter out unexpected events. And my third example here is the whodunit film. You have a detective coming into a living room of a mansion, and he sees a dead guy on the floor, and he's saying, clearly somebody in this room has murdered Lord Smythe. Each of you tell me your whereabouts. The maid says, I was polishing the brass in the master bedroom. The butler says, I was buttering his lordship's scones. And Lady Smythe says, I was planting my petunias in the potting shed. And the detective very cleverly says, Constable, arrest Lady Smythe. And she says, but how did you know? And he says, Madam, as any horticulturalist will tell you, one does not plant petunias until May. But what's going on? Why didn't the CTM see the many changes? For example, the detective's coat went from dark to light, and the dead guy then changed his clothes and his knees up off the floor, and all the flowers have changed, and many of the pictures have changed, and so many things have changed. So detecting change in the whodunit video would have required significant changes in the gist describing the beginning and ending scenes. But size limitations on conscious content and the clever scene transitions cause the high-level descriptions to be essentially the same. So we're saying limitations on the conscious content. Now, that's where we're getting something about resource limitations. We want these chunks to be very small, so our competition will be pretty quick, whatever, and so forth. So the same gist describes the first scene and the last scene. The scene is a living room of a mansion with butler, maid, detective, and a man laid out on the floor. So it's the same succinct gist that describes both scenes, and also a clever production where you're not seeing the transitions, you're going from one scene directly to another scene. Okay, again, this is consistent with the literature. Okay, so those are kinds of examples, and we have many of those. And you might ask, why would a robot with a CTM feel as conscious? And I'm not going to go into this. It will requires a little bit more, and I want Manuel to have his word in. Okay, and this is really related to what's called the hard problem, the feeling of consciousness. The conscious awareness may be part of what's called the easy problem, but the hard problem is the feeling, and we think the hard problem will follow from the easy problem. But what's important here is having a number of specialized processors. So, for example, the inner speech processor when you talk to yourself, and very, very importantly, the model of the world processor. And I won't go into this, but the model of the world processor is sort of a cartoonish version of the model of the whole environment that we make inside our head. And we have an inner world, a model of our inner world, and a model of our outer world, and we label these things with very succinct gists. The model of world processor maintains models of the world of the CTM in these worlds, and the processor serves as many purposes. It figures in exploration and exploitation of this world, and in planning in general. So it'll make plans, send information out. Why don't you do this? It'll get feedback in, and that will change its model of the world. It's how the CTM, the Conscious Turing Machine, understands itself and its place in the world. And I won't go into more detail about this now, but I would like now to end with a comparison of our model and the way Bars had originally modeled the consciousness. So both of us have this tiny short-term memories, to call that working memory, short-term memory, the stage. We both have the audience, the long-term memory processors. But what Bars does is he has information coming in from the outside world going right to the stage. And he has information going out to the outside world right from the stage. So he's having the stage very, very complicated. We're not doing it. Our stage is just a broadcasting mechanism. So inputs are going directly to the processors that they deal with, and outputs are coming directly from processors that the actuators will have to deal with. And in fact, if you look at the literature, this is very much like actually what's happening in the brain. And Barr's model, again, the conscious event is between the input and the short-term memory. In our case, the conscious event is the result of the competition in the broadcast. So it's a little different. There's no specific method in Bars for long-term memory information to get into short-term memory. We have a well-defined competition, which I sort of indicated to you, for chunks to get into SDM. And then importantly, Bars and many others require a central executive, and we do not. We have no central executive. This is all distributed. And this is really critical. It's really important for how our machine, the CTM, works, and it's particularly important for our application of AGI. And so I'm going to take 2 seconds to just indicate what the application is here. So suppose our CTM, which is having inputs from the outside world and outputs and all sorts of things, has some problem that it really wants to solve. It really wants to solve, of course, what we all want to solve is the PNP problem, but we might not be that ambitious, but let's just look at that problem. But our CTM has no idea which processes it's going to go to ask about solutions to this problem. This is a little like what they call a Poincaré effect. Okay, it doesn't know where it's going to go. So one of the processes, when we say the CTM has a problem, it's really because one or several of its processors has this problem it wants to solve. And those processes, or a processor, puts that information into the competition, gets it into short-term memory and says, hey, help me solve the PNP problem. Okay, so what's happening, since all the processors are getting that information, maybe some processors interested in it, maybe have some specialized logic or math thing or algebraic geometry or other things that it's interested, or it has the time to work on it or the inclination or whatever. So those processors will start to work and form coalitions, and then every so often one processor will send up to short-term memory, hey, I'm using this method, here's the part of my proof, I want you to check it. Another processor might check it. So this kind of information is, even though we don't know where it's coming from or who's going to be able to solve it, but we know that there are some processes there, particularly if we add in a lot of very, very special processors like ChatGPT and all such things into our long-term memory, we will have a lot of very specialized, very powerful processors there, but we don't know which ones will actually solve the information, solve the problem. So this is a way of broadcasting and not having a central executive who's deeming who, what, where is going to happen, and that would be very limiting. So this is unlimiting. It frees the CTM to be an artificial general intelligence solver. Okay, so thank you, and that's the end of my part. We have a number of papers. We have an insights paper on PNAS, and we have a free will paper in archive, and a paper just came out. You can get on Science Direct on this perspective on consciousness and AGI. And now I'll leave it to Manuel, and hopefully his slides will come up. And happy birthday again, Russell, and hello, Manuel.
I don't know, Lenore, if you can hear me, but I thank you very much for that explanation. I really, very nice. A model of consciousness, because that's what we're working on. And thank you very much for having me here, Russell. It's great to be here. So about Russell, I just want to tell you that a few things. The only person I know that writes up his slides for a conference half an hour before his talk, while the person before him is talking. It's amazing how many times I've come in and seen him there writing up those slides. It's wonderful to see you doing it that way. I can't, but you do. His wife, Beth, is a poet, quite a good poet, I might say. And you should ask her to recite one of her poems for you. It's quite good. Russell, let me just mention that Russell has written a one-page note on meeting a member of our community while he was a freshman at Wesleyan. It's a one-pager, it's a beautiful one-pager, and gives you a very good sense of Russell and also of Stephen Rudish. As a teacher, his students rate him awe. This is one of their slides, awe, awesome, awful, awfully good. This is a frequent saying I've heard say, a meal without meat is like a story without words, a song without music, da da da. It's okay, so why bring up consciousness in a complexity workshop? So historically, theoretical computer science has defined many seemingly undefinable concepts, like that of pseudo-random number generator. Absolutely amazing. Pseudo-random number generator and zero knowledge proof. These are amazing concepts. So consciousness gives us other concepts which are very important. The feelings, emotions are not clearly understood, certainly not defined mathematically. We believe that good formal definitions can help us understand these important but vaguely understood concepts. So we, Lenore and me, firmly believe that formal definitions are possible for the concepts that arise in consciousness studies, and that our community of complexity theorists, you, can investigate those concepts when properly defined for their consequences. So what is consciousness? So informally, you are conscious of what you see. You talk to yourself? Do you hear yourself talking to yourself? Some people don't, but most people do talk to themselves. What you are conscious of, you are conscious of what you see, hear, and taste. Your inner voice. Your inner voice, your pains and pleasures, your dreams. When you dream, dreams are very important in this whole business of consciousness. Just think of it. If you, not everybody remembers their dreams, but if you remember them, just think. You may imagine yourself in this this auditorium, and that image is created by your brain. It's stored there. It's stored there, we say, as in this brainish gist. Formally, conscious awareness by the CTM. Oh, yeah, so dreams. So the amazing thing about dreams is that you get a sense of the brainish language, what that brainish is about, because it's producing that dream. You have no input from your eyes or ears. You have no output. If everything's working right, no input, no output. Everything in that dream is entirely created by your brain. Dreamless sleep, on the other hand, is an example of something that you're not conscious of. It's a lot that you're not conscious of. Formally, conscious awareness by the CTM, our model of consciousness, is defined as the reception by all processors of the global broadcast from STM. There's a good reason for defining it this way. First, every processor receives the broadcast. Every processor receives that broadcast. So if any processor is responsible for that feeling of consciousness, it receives that broadcast. It knows about what's going on there. And certain special processors turn out to be particularly important for that consciousness. And Lenore mentioned the model of the world processor as an example, but the inner speech processor is another. That model of the world processor has special responsibility for distinguishing self from not self, living from not living, conscious from not conscious, and eventually it has pulled you out as being conscious and the rest is not. Now for the million-dollar question, can a robot with a CTM brain be conscious in the sense that the word is normally used? Can a robot be made to feel pain and pleasure, not just simulate those feelings? Right? You can see YouTube videos of processors which appear to be terribly afraid of a Red Bull or something like that, but these, you know that these are simulations. The question is, can you actually get that robot to truly feel that? The easy problem is to make a robot that simulates the feelings of pain and pleasure. The hard problem is to make a robot that really feels that pain and pleasure. So Lenore showed you our model of consciousness, and there's this question, how do we check the correctness of this model of consciousness? Or more generally, any model of consciousness. So mathematicians, it's wonderful in mathematics, you have a way to check your ideas. You check it with proofs. And physicists have a way to check. They also use proofs to help, and they check with experimentation. How are we modelers of consciousness to tell if our theory of consciousness is on the right track? Now, this is a hard problem because it's not clear what consciousness is. You can't tell, you know, the only reason I know that you are conscious is because I know that your brain is built like mine and I'm conscious, and therefore I think you are conscious too. But otherwise, how do you tell? And which animals are conscious? Okay. Modelers of consciousness need to know if they're on the right or wrong path. How are they to tell? And in general, I don't know how they are to tell. I'll tell you how we, Lenore and I and Avram, are making that decision. We assume we're on the right path with CTM because the model generally and repeatedly reflects our intuition. Very important. And of course, sometimes it doesn't because the model is very simple. But we require that to be on the right path. We assume we're on the wrong path when our model needs repeated revisions again and again. Then we know that, and our definitions are too complicated. Okay. So about consciousness, we tried many models. We really wanted a deterministic model. We worked very hard to get a deterministic model, but the deterministic models all crashed. We wanted deterministic model because we were interested in free will, the free will problem. And we have a paper which gives our explanation for it. But the point is, we wanted to show that even in a completely deterministic world, it doesn't matter that this world is not deterministic. If the world were like one of these the game of life type of world where everything is completely deterministic, we wanted to show that even in that world, it's possible the machines would have free will. And so we really wanted that deterministic model. So in the, but the deterministic models all crashed. All crashed means that we found that we had to again and again change the model. We needed an explanation and we couldn't do it without modifying the model. And we did that so many times that we clearly, it was something was wrong. It was just getting too complicated. And the wonderful thing is that when we turned to the probabilistic model, everything fell into place. The model became simpler and all the complexities we had, and it just amazes us how lovely that model is. So the model, the probabilistic CTM solves many problems, and here's one such problem. In the deterministic CTM, a gist of weight 9 always beats a gist of weight 8. And the CTM remains conscious only of the gist with a higher weight, gist A. In the probabilistic CTM, when gist A, B, C have weights 9, 7, and let's say 0 for all the others, the probability that A reaches STM is going to be that 9 divided by 9 plus 7, 16, and the probability that B reaches will be 7/16. This means that the CTM is conscious of A about 9/16 of the time and conscious of B about 7/16 of the time. And there are a bunch of examples which I won't go into, you know, no time. So about consciousness, yeah, did this. So how the uptree competition works when CTM is deterministic. So in the deterministic case, for example, here's a very simple case. There are four processors with weights 10 each. In the deterministic CTM, the chunk with greatest weight wins. And if you have several chunks having the same weight, the one with lowest address wins. So here, A beats B because it has a lower address, and then it beats C because it has a lower address. A wins. And as long as the weights don't change, A wins. So for many, this is just one little example of how the deterministic model fails. Here's the example again. I put my favorite numbers at the bottom, 3.141592. Yes, and you see here that A will beat B because the weight of A is 3 and the weight of B is 1, so A moves up. A will beat C because A has weight 3 and C has weight 4, so C moves up. Eventually, F is what gets up to the stage because it has the highest weight. You might think that this is a great way to do it. It's not. Let me just mention here that these weights, by the way, they add up to 31. And this will turn out to be important because what we would like is for the weight for A to have a probability given by its weight, 3, divided by the sum of the weights. We want that probability to be what gets to the top. You might say, well, it sounds kind of natural, kind of what you might like, but is it really absolutely necessary? Well, the point is that if the probability of A getting to the top is just its weight divided by the sum, if it's just that, it doesn't matter where A is. And it's this that enables these processors to be moved around, and there will be no change in what actually gets up into short-term memory. No change at all. Which, as Lenore pointed out, is kind of nice because our cortical columns can't be moved around. By the way, these tournaments. So you see these tournaments in chess and tennis, and in chess and tennis, you don't get this kind of thing. Here's A with a weight of 3. In a normal tennis tournament, whether A beats B or not is probabilistically determined by its weight, right? If A has weight 3, you see in that gray zone, A has weight 3, B has weight 7, then the probability that A will win is 3 divided by 3 plus 7. So we would like that to be the probability that A wins at the top, but it's not. In the chess and tennis tournaments, what gets of which this is an example, you see that A is getting up to the top with probability 0.135. So, something you can calculate. Good, you did. And but that 0.135 should really be 3 divided by 31, which is 0.097. So you see, this is not quite right. A is getting up to the top with a probability greater than it should have. And if you look at F, it's getting up there with probability 0.31, whereas it really should be 0.2. So one of the questions is how do you manage to get these chunks going to the top with the right probabilities? Okay, so by the way, these probabilities are not so easy to calculate. You'll see very easy to calculate it if you have intensity and mood. So, so here, what you do is, as Lenore mentioned, intensities add. The intensities are initially the weight of A, absolute value of the weight of A, and is the intensity. And A will beat B with probability 3 divided by 3 plus 1 is 4. But after that, in the CTM, the way we use this is that A, which won, if it won, will have the intensity, which is the sum of the intensities of it and the player it was playing against. So 3 plus 1 is 4. So the intensity after A plays B, whichever wins, the intensity will be 4. And A will, or whichever wins there, will then play whichever one the other will choose, which will have an intensity of 5. So what gets up to the next level, well, A will get up to the next level with probability given by its intensity divided by the sum, 4 plus 5, 9. And so now the probability of A getting to that second level is the 3/4 that it had to get to the first level, times 4/9 to get to the next level. And then at the very top, you see that the probability that A gets to the top is at 3/4 times 4/9 times 9/31, because see 9 divided by 9 plus 22 is 31. You see it's 3/31. Isn't that nice? Very easy to calculate, and it's lovely. And tennis and chess do not do this, but our CTM does do it. Okay, so see what else. So we go to all this trouble to ensure that for every processor X, chunk X wins with probability equal to its fair share. And the corollary, which I've already mentioned to you, in the CTM, the location of a processor has no effect whatever on what gets broadcast from short-term memory. Okay, this is an example of something that convinces us we're on the right track. The simplicity here. Now, for another example that convinces us we're on the right track, for this, I'll want to talk about additive competition functions. Competition function is this F, which is used to decide do you go, the probability that A moves up is given by its F value divided by the sum of its and its opponent's F value. So we need to say what makes a competition function additive. An additive is drawn here as, so you have a chunk on the left and you have a chunk on the right, and one of them wins and goes up, and the chunk that moves up will actually be described as the left chunk plus the right chunk. It's that chunk, that blue chunk that comes from the left chunk and the right chunk will have the original address of the processor that generated it, the gist, the weight. What will happen though is that intensity will add and moods will add. So competition function is additive if and only if f of the left plus f of the right is equal to f of the left plus f of the right. Here's additive competition functions. So the top right shows diagram is showing you that definition. And the theorem is that if f is an additive competition function, then the probability that processor PI's chunk reaches short-term memory is exactly what you want. It's the fair share. It's that f value of that processor divided by the sum of all the f values. And the corollary is that if f is additive, then the chunk that reaches STM is, as now I said several times, independent of the assignment of processors to the leaves of the tree. Additivity is nice for doing arithmetic, but it's really much more than that. We have a theorem that if it's easy to show that okay, so f is an additive function of intensity and mood if and only if f of the chunk is equal to essentially the intensity plus a constant times the mood, and that first constant, just think of it as 1, but the red constant, the C2, runs between -1 and +1. And this is an if and only if. This is the right definition, the most general additive function that will work. So of course we like that. We have finally some notion. Let's see what that means. And this is makes us very happy, because it turns out that if that constant in front of the mood is positive, well, let's look at what happens if that. If it's positive, we're going to say it's the CTM is optimistic. If it's negative, we say it's pessimistic. Let's actually look at the most optimistic and most pessimistic examples. If C2 is equal to 1 plus 1, then we say that CTM is manic. And why is it manic? Because look at the very bottom. You have two processors, and say the weight of one, the weight is some positive value like 3. Well, intensity plus the mood, if the constant is 1, it'll just doubles the intensity essentially. But if you have an intensity of +3 and of -3, and with constant of +1, and if the weight is -3, the intensity will be 3, the mood will be -3, they add up to 0. So in the case where the constant C2 is +1, the CTM does not see anything that's negative, nothing. It sees only what is positive. If you know some manic depressive people, you will know that this is what happens. You know, manic depressives, they can they see only what's positive. They can lose their money, their house, they can lose everything. As long as there's anything positive, they're excited and they're positive and they think things are wonderful. It's only when there's nothing positive, there's every single thought is negative, that suddenly it's forced to look at something which is negative. And in the model, it's forced to, and it simply jumps around. And this is exactly what happens with manic depressives. When they get manic, it's wonderful. They're up in the clouds, and then at some point they drop down into terrible depressions. Everything's suddenly become negative. Okay. Where are we here? See, so I wanted to have a place where we could end this talk, or we can keep on going. For how much more time, if any? Okay. Let me go. Okay, so we'll. So one of the things is we focus on pain and pleasure. The feeling of pain. For me, the feeling of pain is an absolutely amazing thing. You know what, some people say, well, pain is an illusion. Well, you can't convince me that pain is an illusion. So Lenore and I divvied up this problem. I spend all my time thinking about pain, and she spends all her time thinking about pleasure. I've never had that question before. That's wonderful. Thank you, Russell. That's great. So we would like to understand these, and you can understand the problem if you know about this condition called pain asymbolic. Pain asymbolic is very interesting. A person can get knocked on the head, and after that knock on the head, get pain asymbolic. They will know about pain, but they will not suffer from it. They simply will not, it does not cause the suffering. You might think, ooh, isn't that wonderful? Maybe, but the kids that are born with pain asymbolic don't live past the age of 3, because they don't have that suffering to actually guide them. And so the question we have is, well, what's missing in that brain that gives you the feeling of pain? And you could ask the same for a robot. What's missing? What is it that's missing in the person? What's missing in a robot to give it that sense? So how might a robot with a CTM brain feel pain? This is sort of the crucial question, really. What is generating that feeling? We have only 2 suggestions for that feeling of pain. We looked and looked, there are only 2 suggestions for it. One is the broadcast. Extreme pain, I'll look at extreme case, the others are easier. Extreme pain is this actor that takes over all STM. It prevents all other actors from reaching the stage. It's the thing that's broadcast, and no processors can know about the pain. And with few exceptions, nothing else can get into short-term memory. And there's confirmations. Under conditions that normally cause agony, pain asymbolics can think, while normals cannot. If you're in pain, you can't play chess, but pain asymbolic person can play chess. In the Darwinian design, you might expect pain to lead to constructive thinking, but agony actually interferes with constructive thinking. That's what's going on here. What? How does this help? For one, it stops you from doing what you're doing. You simply can't keep on with what you're doing. Does stopping what you're doing apply as well to low levels of pain? So here's a paper on the impact of persistent pain on working memory and learning participants that identified as experiencing low levels of pain for over 6 months performed significantly worse than pain-free participants on a variety of tests. So even, yes, that's the bad thing about having pain. It doesn't let you use your brain to the fullest. And then there's brainish. The other thing about that feeling of pain is brainish. The multimodal language that processors use to broadcast and communicate among themselves screams pain. I don't know if it turns out that, have you ever had a dream, dreamt that you had a pain? It turns out that not everybody has. Some people have dreamt they had a pain and they woke up and they had a pain. Really, they did have a pain. But it's also possible, and I've had this experience of taking a nap, having a terrible pain in my leg, and the moment I wake up, it's gone. That pain was completely created by the brain. And it turns out that it shows you the power of the brainish to create a gist of pain. And there is the feeling of physical pain during dreams carries over into waking in about 5% of people. About right. So there are other things that come up, and very interesting. This Thich Quang Duc would burn himself to death. That's a terrible pain. How could he do that? It's very interesting to look into that. How are these ideas to be checked? Here, the CTM is a simple mathematical model. Our goal is to freeze the model and explore it. We don't want to change the model. We taught a course in Peking University in which the students were told to try to find something that the model does not explain, and to try to come up with a change that you need in the model. And it's wonderful that they managed to do this without that. In the end, every example they came up with could be done with the model as it stands. And this really is the end.